Okay, so next we are going to see about the important concept interrupts. Okay, have you heard about it? Okay, that's most important. You'd have heard, but little meaning you know, but the technical meaning here is, so normally the CPU will proceed with the normal execution of the program. So you'll have some application program that you have written in the memory. The CPU will start to execute it if something or something in the sense some event. So some event disturbs the normal execution of a program, that is called as an interrupt. Fine. So generally the interrupts are nothing but an event that disturbs the normal execution of the program. Fine. So as I told you, it's nothing but an event that disturbs the normal execution of the program. Okay, fine. Okay, so if I would say you an example, now I'm teaching you, I'm lecturing you. Okay, fine. So if somebody enters in this room, I have to stop where I am now. Okay, and then I have to respond to a person who is entering in this hall. Okay, after responding to him, then I have to continue with my video lecturing. Okay, so here I'm lecturing, no, so that is the normal execution. Fine, that is what happening regularly. Fine. So if somebody enters in this room, that is the interrupt. Fine, who is nobody is. If somebody enters the room, that is an interrupt now. Fine. So I am responding to him, and after I am continuing with the work where I have stopped. Fine. So this is the whole operation of an interrupt. So likewise, the CPU will also do. Okay, fine. So if the CPU is executing a program, fine. So for example, I will give you this program as an example. The same program that we discussed in the previous lectures. Okay, so for example, this is an instruction. Your processor is executing the instruction line by line. Okay, at this line, when the processor is executing this instruction, if an interrupt occurs, what your processor will do is completes the execution of this particular instruction. Okay, it completes the full execution of this instruction. Okay, later it jumps to the interrupt program. Okay, it will jump to the interrupt program. So which is stored in some other location which is not related to this one. Okay, it will jump to some other location to execute this interrupt program, finishes the execution of this instruction, and return back to the line where it has been stopped. So it has stopped here before STA, so it will return to STA to execute this instruction. Okay, this is how the execution takes place. Fine. So each and every interrupt is have an predefined memory location. I told you, no, if an interrupt occurs at the execution of this instruction, it jumps to a memory location where the interrupt program is stored. That I have told you, no, this memory location is predefined. Okay. Okay, for each and every interrupts, it has a predefined memory location. Okay, such kind of interrupts with predefined memory locations are called vectored interrupts. Okay, which is nothing but interrupts with memory location. Okay, specified memory location. So that memory location is dedicated for that particular interrupt and not for the other interrupts. Fine. So in that memory location, we will write the program. Fine. So that interrupt program is called as subroutine. Okay. And after executing this subroutine, it will return to the program, main program, and to the line where it has been stopped its execution. So this is how the interrupt operation will takes place. Fine. Another concept is also there in interrupt, that is nothing but polling. What polling is? The CPU, which is nothing but your processor, will looks or monitors the status of the device that is connected with your processor for an interrupt continuously. Okay. So for example, if I take your mouse is connected with your processor, fine. Okay. So with some it will be connected with some pin number, no? So what your processor will do is, if you assign it with polling, it will monitor the pin number where the mouse has connected continuously. Okay, fine. For an interval of time, it will be monitoring it whether the device needs the service of the CPU or not. Okay. So which is a disadvantage as you compare with interrupt. Why it is disadvantage in the sense? So interrupt, it will occur only if the peripheral device needs the CPU service, it will indicate the CPU with an interrupt signal. So then only the processor, that means nothing but your CPU, gives its service to that peripheral device. So now as of here in polling, what will happen? The CPU spends its most of time in monitoring the peripheral device, whether it needs the service or not. Fine. So that is a disadvantage in polling. Instead of using polling, in most of the applications, we will use interrupts. Fine. So polling is nothing but the processor will continuously monitor the status of the peripheral device. Fine. So this will consume more time. So that is the most disadvantage of polling. Fine. So the next, so now we all know what is subroutine, vectored interrupt, polling interrupt. Okay. So now we will see about the maskable and non-maskable interrupts. So first we will see about the maskable interrupt. So maskable is nothing but the interrupts that are controlled by the program itself. So program in the sense is nothing but the values that we give to the registers that will control the execution of a program. So if you consider an interrupt as maskable, then even the interrupt occurs. Okay. If you mask it, the processor does not execute that interrupt. Fine. So for example, if I say that maskable interrupt, okay, so consider that interrupt 1, okay, no such interrupt exit, for example I am saying, okay, interrupt 1, it occurs, okay, but what you have done, okay, using a register you have masked this interrupt. Interrupt 1 was masked. Okay. So if it is masked, if it is not masked, consider that this masked concept is not there. So if an interrupt occurs, what will happen? This interrupt will have a memory location where the subroutine will be there, no? So immediately processor will stop the execution, jumps to this memory location, executes the subroutine program, then it returns to the program where it has been stopped the execution, right? So this is what happened normally. Okay. So if it is not masked, so now consider this interrupt is masked, which means that it is a maskable interrupt. Okay. So what will happen now is the processor does not execute this subroutine. Okay. So which means that it is masked. The interrupt has occurred. The processor is supposed to execute that program. Fine. So now since it is masked, the processor does not execute the program. Fine. So that is the concept of maskable. Okay. So here in our 8085 we are having both maskable and non-maskable interrupts also. Fine. So next we will see about non-maskable interrupt. Fine. So maskable interrupts you can enable or disable it using the program. Fine. So non-maskable interrupts you can never mask it. Okay. Whenever that non-maskable interrupt occurs, you have to proceed with the interrupt procedures. You have to go move on to that memory location, execute the program that stores in that. Fine, you have to continue with the procedures. You can never mask that interrupt. So such kind of interrupts are called as non-maskable interrupts. Fine. Okay, now you know about maskable and non-maskable. Okay, fine. So next we will see about the hardware and software interrupts. Okay, first we will see about the software interrupts. So software interrupts are nothing but you all now familiarized with the interrupts procedures, no, how it occurs and what happened after its occurrence. Okay, so that procedure don't forget, remind that. So software interrupts are like the instructions. As an instruction we are providing an interrupt. So this we have seen while we are discussing about the instruction set itself. So do you remember while we are discussing about the branch instructions? Okay, what we have discussed in branch instruction? Jump, call, then call and return, then restart. Fine, do you remember that? Restart. So RST 0 to RST 7. We are having 8 software interrupts. Fine. So for each and every RST 0 to RST 7 is as a specified memory address. Do you all remember that, no? Okay. So now you remember, no, RST 0 to RST 7. So this is called as a software interrupt. So each and every interrupt is having a specified memory location. So 0, 0, 0, 8, 1, 0, 1, 8, 2, 0, 2, 8, 3, 0, 3, 8. Okay. So since each and every instruction is having a separate memory address, these interrupt memory address are known as vector address. Don't forget that. Okay. So these interrupts are called as vectored interrupt. Fine. Okay. So and this is the hex code, which is nothing but opcode of these instructions. So when you provide the interrupt as a program, as in the program itself as an instruction, so that is called as software interrupts. So okay, either it can be a software or hardware interrupt, but the procedure is same. It will move on to a specific location, execute the subroutine and return to the main program where it has been stopped. Fine. Okay, so in the previous lecture itself I have told you how these address lines are derived. So with the vector number into 8 will give you the vector address. The numbers are nothing but 0, 1, 2, 3. Multiply this with 8 and you can derive the vector address. Okay, so now we will see about the hardware interrupts. So as we have discussed, software interrupts in the program itself as an instruction we will give. So hardware interrupts, oh yes, we will give as a signal in the pin itself. Okay, so as we have seen, how many pin IC is this? 8085? Yes, it's a 20 pin IC. So in that, how many hardware interrupts are there? We have discussed before. Yes, 5 hardware interrupts. Do you remember? Yes. So those interrupts are hardware interrupts. What are they? Trap, RST 7.5, RST 5.5, RST 6.5 and interrupt request. These are all the 5 hardware interrupts, which is nothing but we can give signal through the pins. We are having a pin called these interrupts. Separately we do have these pins through which we can give our interrupts. So we will see this hardware interrupt one by one. Okay, so I will explain each and every interrupts now. So this is the interrupt structure for those 5 interrupts. Okay, so since we have 5 hardware interrupts, each and every interrupt has been assigned with a priority. Priority is nothing but giving preferences. Okay, fine. So since we have 5 different hardware interrupts, if any 2 interrupts occurs at the same time, the processor will have a confusion that what interrupt it has to execute at the first. Okay, so for example, we are having trap and RST 7.5. If these 2 interrupts occurs at the same time, your processor will get confusion what interrupt it has to execute first, either trap or 7.5. So to avoid that confusion, each and every of that 5 hardware interrupts is assigned with the priority, which is nothing but preferences. We will see that order also. Okay, so first we will see about the trap. Okay, here it is, trap interrupt. So this trap is having the highest priority 1. Then the other interrupts, trap is having the highest priority. So if at this case that we have discussed before, if these two interrupts occur, processor will first execute this interrupt, then only it will comes to RST 7.5. Fine. So this interrupt, as we have seen, this is a pin, right? So at this pin, if we have a signal, it will consider as an interrupt. So the signal will be like this, it will be like pulse. So at which range of pulse, this processor will consider this signal as an interrupt, in the sense as in the edge or level. Okay, that's why it's called as edge triggered, level triggered. Fine. So you can assign it as an edge trigger or level trigger. So what mean by level trigger, in the sense, in this signal you are having two levels, one is low level, another one is high level, right? So this is low, 0, and this is 1, high level. Fine. So either you can consider at the low level. Okay, so whenever the 0 comes, you can consider an interrupt occurs, or whenever this high pulse comes, you can consider the interrupt has occurred. That is called as level triggering. You are considering only the levels. Okay, so next is, this is level triggering. Okay, and next is edge triggering. Okay, so if you consider this as your pulse, what are the edges it have? This is positive edge and this is negative edge, right? Positive edge is nothing but low to high level. So this point is called positive edge. Then when it moves high to low, this is called negative edge. Okay, so whenever your processor faces a positive edge, you can consider an interrupt occurs, or whenever the negative edge comes, you can consider that as an interrupt occurs. Okay, this is called level triggering and edge triggering. So for trap, whenever you have a signal, you can program either as a level triggering or edge triggering, that is mentioned here. Okay, so trap is a non-maskable interrupt. What do you mean by that non-maskable? What do you mean by that non-maskable? So even though you cannot mask this trap interrupt, whenever this occurs, your processor has to execute its subroutine. Fine. So this trap interrupt is a vectored interrupt, which means that a specific memory location is assigned for this interrupt. So that location is 0024. Fine. Okay. So in this diagram, the interrupts are explained here, and this is the vector locations of these interrupts. Fine. So the next prioritized interrupt is RST 7.5. The highest priority is trap, and the next one is RST 7.5. It is a positive edge triggered interrupt, as we have seen. So only it will consider the positive edges. So whenever the positive edges come, it will consider an interrupt occur, not at the negative edge. Fine. So its vector address is here 003C, and it is a maskable interrupt, that is most important. Fine. So RST 7.5 is a maskable interrupt. Okay, and it's a vector interrupt also. Its address is 003C. So the next interrupt is RST 6.5 and 5.5. Both of things are level triggered, which means that either you can do a high level or low level. Fine. So these two are also vectored interrupts. Okay, that address are mentioned here. Fine. Now you got about RST 6.5, 7.5. So the next interrupt is interrupt request. Fine. It's a level triggered interrupt, maskable interrupt, and it is not vectored interrupt, which means that it does not have any memory location. So when you mention this interrupt request, you have to the programmer has to mention the memory location for this interrupt request. Fine. So as I told you, INTR, which is nothing but interrupt request, is not a vectored interrupt. So the programmer has to mention the memory location there. Fine. Okay. So once again we will summarize this hardware interrupts. So the hardware interrupts are trap, RST 7.5, 6.5, 5.5 and interrupt request. So in this the most highest priority is given to trap. Next is RST 7.5, then 6.5, then 5.5, then interrupt request. So in this the non-maskable interrupt is trap only. Other interrupts are maskable interrupts. Fine. So in that the one and only non-vectored interrupt is interrupt request. So in this the trap and RST 7.5 is edge triggered. Other interrupts are level triggered. Fine. So that's all about interrupts. Okay. As of now we have seen the timing diagram and interrupts. Later lectures we will see about the memory and IO interfacing. Fine.